Good morning, Algebra 2. For this section here, go to my Canvas page and look at the key. Fill in some blanks. There's quite a bit of blanks to fill in on these notes today. So any of these blanks that I skipped, just go to my Canvas page. Look up the how to fill them in and do so accordingly. All right, let's get to solving some of these problems. Graph the following. This is written in vertex form. Your vertex is -1, comma, 3. So that's the very first dot that we are going to plot. Let's go left one, up 3. 1, 2, 3. Since there is no number in front of those parentheses, that means we do not have a stretch or a compression. So we can do that trick I showed you a unit or so ago. To plot our next dot, let's go right 1, up 1, right 2, up 4. And then from this dot, we are going to go right 3 and up 9. And then we're going to mirror that on the left side of the vertex. Left 1, up 1, left 2, up 4, left 3, up 9. Now this is a inequality, so we're either going to connect these dots or they're going to remain dashed. Since this is not a equal to statement, let's make sure they're dashed. We also have to do some shading. All the values where y is getting greater are this direction, and so we want to shade above the vertex. And there's your answer for that one. Example 2, our vertex here is 5, 1. So that's where we're going to put our very first dot. Right 5, up 1. There is no stretch, there is no compression, so we can do the same thing we did with the previous one. Right 1, up 1 from the vertex. Go back to the vertex, right 2, now up 4. Back to the vertex, right 3, and then up 9. And then points opposite of the vertex are going to mirror one another. This is a equal to statement, so we want to make sure and make this solid. Since this is a less than, you want to shade below your vertex. So all this area outside of our parabola would be shaded. Example 3. Our vertex here is 0, comma 5. So from the origin, go 1, 2, 3, 4, 5. Now, if we look in front of x squared, we do not have a stretch or a compression, but we have a reflection over the x-axis. So this time from the vertex, we're going to go right 1, down 1, right 2, down 4, right 3, down 9. And I'm going to stop there. This is a equal to statement, so you want to make sure this is solid. And since it is a greater than, you would want to shade above the parabola. Everything outside here. The next example, that's not written in vertex form, that's written in standard form. So we're going to have to use this formula to get us started. X equals -b over 2 times a. That's going to help us with our axis of symmetry, which will ultimately help us find our vertex. So -b over 2 times a. So -4. Okay, so that's our axis of symmetry. X equals -4. That's our axis of symmetry. That's also half of our vertex. We know the first value of our vertex. To find the missing value, we're going to take -4 and we're going to substitute it for x back into our function here. And then start simplifying. So it looks like when x is -4, y is 4. That's our vertex. So let's plot that point. Now there is no stretch, there is no compression, but there is a reflection over the x-axis. So our graph is going to be opening down. So from the vertex, right 1, down 1, right 2, down 4, right 3, down 9. This is not a equal to statement, so keep this dashed. And this is a less than, so you're going to want to shade everything below the vertex, all this here. Okay, move over to side 2. For situation 1, I'm not going to be graphing this one. We're going to be solving these algebraically. And here's what you need to do. You just need to set your two equations equal to one another. So I'm going to do x squared plus 4x minus 5, and we're going to set that equal to x minus 1. Once again, we just took our two functions and set them equal to one another. And now we're going to set the equation equal to 0 by combining like terms. And now we have a trinomial that we can factor. There's the factors that we need to use. Since the leading coefficient is 1, you can go ahead and go right to factored form. No need to group here. Just saves yourself a little bit of time. And if you were to set each of these equal to 0 and solve, here you'd have to add 1, and here you'd have to subtract 4. Now, for our answer here, we're going to have two sets of ordered pairs. The x value for one of them is going to be 1, and the x value for the other is going to be -4. We don't know the y values yet. What we have to do is we have to take each of these separately and substitute them back into either one of the functions. It doesn't matter. I would choose the easier one. So I'm going to substitute 1 into this function first, wherever I see an x. 1 minus 1, that's 0. So an x is 1, y is 0. And now this one here, let's substitute -4. When x is -4, y is -5. So these are our solutions right here. Now, as I mentioned, I'm not graphing these, but if you were to graph them, guess where they'd meet? They would meet at these two sets of ordered pairs. Situation 2. Once again, I'm not going to graph this one. We're just going to solve algebraically and see what happens. Let's set these two functions equal to one another. Now that they're set equal to one another, we are going to set it equal to 0 by combining like terms. Okay, we once again have a trinomial that we can factor. The leading coefficient is 1, so you can go right to factored form. And if you set each of these factors equal to 0 and solve, you get 1 for both of them. So in this scenario, x equals 1. We got the same answer. Now that we know the x value is going to be 1, we're going to take this 1 here, and we're going to substitute it into this function there. And we're done. if you were to graph these two functions on your xy coordinate plane, they would meet once. They would meet at the coordinate 1 comma negative 6. And then the last one, situation 3. I am going to graph this one because this one's going to be a little bit different. If we graphed this one here, oops, I actually started by plotting it wrong. Ignore that dot right there. The y-intercept is -1, not +1. So yeah, I need to start there. This is the bad copy. I can't even tell where it's supposed to go. And once again, please ignore that dot right there. I just made a mistake. All right, let me erase it. Yeah, it's gone. Now, if we plot this one here, the y-intercept is -6. The slope is 1, so up 1, right 1, right 1. That's about enough. Now I'm just going to go ahead and connect these dots. All right, so by graphing these, hopefully you're able to tell that they would not meet. Now, this is what it would look like solving graphically. But if you weren't solving them by graphing, if you're using algebra, here's what it would look like. We're going to start the same way we did the previous ones. Set the equations equal to one another. Combine like terms by setting this equation equal to 0. And now we have a trinomial that will not factor. We cannot factor this one. So we'd have to use the quadratic equation. Our a value is 1. Our b value is -1. And the c value is 5. So I'm going to start plugging into the quadratic equation now. And then simplify. I want to simplify inside that square root. We can simplify just a little bit more. And then the last thing that we can do to simplify is I'm going to change that to positive, and I'm going to put an I right in front of the root. So as you can see, our result was imaginary. If you're solving systems like these and you get an imaginary result, that means your solutions are never, your functions will never meet. You'll have a good day.